If you remember last time where we left off, there was this lemma 5, which I had stated but didn't prove yet. And what it says is that the half-order derivative dn of a function f in BMO is controlled by the Carlson norm of a certain measure, okay? Where the Carlson measure, d mu of rxt, this is in the upper half space, is going to be beta squared of rxt dx dt dr over r. And the beta is really beta sub f. Well, let me write the square of it. It's going to be r to the minus d. Remember, d is the homogeneous dimension of parabolic Rn. Integral over the parabolic ball of radius r, centered at xt. And what we're integrating here, whoops, I forgot one thing. We need to take an infimum. And this should be f of ys minus L of y over r, all squared, dy ds. And the infimum runs over all L affine functions in the space variable only. Okay? All right, so this is what we're going to prove next. There's also a converse direction to this, which is that in turn, this expression is bounded by the Lipschitz norm in space of the function f. This is an L infinity norm in x and t, so it's Lipschitz in x uniformly in t plus, again, the half-order time derivative in BMO. Okay, I don't have time to prove this direction. This direction, let me just make the comment. So there's an original proof from some years ago that's based on Fourier analysis. Well, localization to reduce matters to turn the Carlson measure estimate into a global L2 estimate. And once you've reduced it to L2, it's just Fourier analysis, Plancherel. Okay, that's the original proof. But let me add a comment, is that there's a much more recent proof, geometric proof, not going via the Fourier transform, due to Tuomas Orppanen. And that's kind of neat what he did. So if you're interested enough to look this up, you might find his paper more illuminating than the original Fourier analytic proof. Okay, so yes. Yeah, so it's yeah, this is in the paper about something called integral geometric approach to Doran-Soro estimates. Is that the one you had in mind? Yeah, that.
So I was asking if this also gives you a geometric proof of Doran-Soro, but without dependence of time.
Oh yes, yes. If there's no time variable, then it's just the usual elliptic version of Doran-Soro. Yeah. That's right. Yeah. Okay. It's basically the same, only a bit technically simpler. Yeah. Okay. So let's prove this. So what we want to show is that given, I'm going to dualize. I'm going to do this by duality. I'm going to dualize against. Let me not let it be f, because f's taken. Let it be g. I'm going to dualize against the function in the parabolic Hardy space H1. And to make things rigorous, I'm going to let it be a finite linear combination of H1 atoms. Of course, parabolic H1 atoms. That just means that the cubes are parabolic cubes. Otherwise, it's the same usual atomic condition. All right, and we want to show that when we dualize here, this will be less than or equal to this Carlson norm times the H1 norm of G. Okay, usual thing. All right, and so we let PR denote a nice parabolic approximate identity. Which means what? I.e. PR of G equals phi R star G, where phi R of xt is R to the minus D, phi of x over R, T over R squared. Phi is supported in the unit ball, say. By the way, you've probably figured out that the unit ball is the same whether you're in parabolic metric or standard Euclidean metric.
Steve, when you do the convolution, do you do the convolution with respect to both variables, x and t?
Yes. Parabolic, it's the convolution in both variables. Yes. Both space and time. Yes. Okay. And let's see. Phi is going to be C0 infinity. And one other thing, we want phi to be even in x for each fixed t. Okay, so in the future, in these lectures, when I talk about a nice parabolic approximate identity, this is what we're talking about. Okay? Oh, and of course, the important thing is that the integral of phi should be 1. Okay, so that it actually approximates the identity. Yeah, we need that too. Okay, so then let's remember that dn is dt, the time derivative, composed with negative square root of the heat operator. So its adjoint is going to be minus dt composed with the negative square root of the adjoint heat operator. All right. And we then have if we integrate in the r direction, which is going to be our vertical direction, and of course we're using that as r goes to 0, this approximates the identity, and as r goes to infinity, it goes to 0. Okay. All right, and so then of course we do the obvious thing, we distribute the r derivative. And this is going to be minus integrals. We'll have, first of all, dn of dr prf prg plus dn prf dr prg. And I'll split these into two pieces. The integral involving this part I'll call 1, and this part I'll call 2. And maybe to save time, I'll just treat 1 because they kind of end up being treated in more or less the same way. Okay, so for term 1, I'm going to flip this half-order time derivative over here. Okay, so that introduces the adjoint, right? So this becomes I've got dr PR of F, dn star PR of G, and then I have dr dx dt. I guess I've written these in the wrong order, but let's not worry about that. And then I'm going to do the usual thing. I'll normalize this. I multiply this by r and divide by r. Okay? All right, and then there's this classical argument due to Pfefferman, which I won't go through, but you might well be familiar with it. This is basically Pfefferman's original argument, or part of his original argument, to prove the duality theorem, that BMO is the dual of H1. And so what you end up getting here is that this ends up being less than or equal to something I'll call the Carlson norm of mu tilde, and then you'll get the area integral of this guy. And I'll tell you what that is in a sec. And that's in L1. Okay? And the area integral of this thing, let me call this, because this is what we're going to use anyway, let me call this QR of G. All right? So A of QR of G just means the square root of the integral, actually it'll be a triple integral, where x t minus ys is less than r, then we'll have QR g of xt squared, and then we'll have r to the minus d minus 1 dx dt dr. Okay? In other words, it's just, well, oh, I suppose I should, yeah, not erase that yet. Let's do this. You're wondering about the homogeneity, the exponent there? Yeah, it's r to the power minus d minus 1. The dr, the minus 1, that's really, that corresponds to the dr over r measure. And the minus d is because, well, d is the homogeneous dimension, and when you integrate an x in t, you're integrating over a ball of radius r, and that kind of makes it an average. All right? Okay, so the brief comment, without doing all the details, the brief comment is that QR equals R dn star PR is pretty nice enough parabolic Littlewood-Paley operator. Right, because we're putting, in effect, one order of differentiation in the parabolic sense on this nice approximate identity. All right, and so this is really a nice square function, nice parabolic square function being applied to G. And parabolic square functions map Hardy space H1 into L1, okay? So this block A of QR of G in L1 is controlled by the H1 norm of G like we want it. Okay. What about this thing I've called mu tilde? Well, mu tilde, d mu tilde of Rxt is this guy, dr prf of xt squared dx dt dr over r. Okay? All right, and now I claim, so the claim is that mu tilde is less than or equal to mu. And then I'm done. All right? And the reason that's true is because what you notice, remember that the kernel of this guy, phi r, satisfies that the integral of phi r is 1. Hence, dr pr of 1 is 0. It kills constants. But it also kills first degree polynomials in space. Okay? Also, remember, we said that we specified that this guy is even in x for each fixed t. Hence, integral of phi r of x t times x dx dt equals 0, because you're integrating an odd function, an odd compactly supported function. Okay, so also dr of pr of L equals 0 for any affine function, affine in space. Okay? So that means here we get to replace f by f minus L. All right. But maybe let me evaluate this at x and t. Okay. Remember, dr is the dr of pr means we're differentiating this kernel. So this will be less than or equal to an average over a ball of radius r centered at t. When we differentiate the pr, we get an extra 1 over r. So here I've got f minus L over r dx dt. And now I just use Cauchy-Schwarz, and there's my beta. Okay? And that's the proof. All right, any questions? Okay. Again, I've glossed over the term 2 there, but similar considerations work for that guy as well. Okay? All right. Okay. So now we're about ready to move on to the proof of the main theorem. All right. So they still need, in this context, to state one more lemma. All right. So given a fixed surface cube that I'll denote by delta star. Okay, so this is some elongated box I star intersect with the boundary, intersected with sigma. I'm going to set, and for the proof, throughout the proof, we're going to actually specify a fixed one of these and work with this fixed one. Okay, so I'm going to set omega to be a normalized version of the caloric measure normalize with respect to this guy. So I'm going to normalize it by multiplying by the sigma measure of that. I should give myself a little more room because I'm going to run out of, I'm going to crowd this a little bit. So this is going to be omega is sigma of delta star times the actual caloric measure with pole at the time forward corkscrew point relative to delta star. Okay? And omega tilde, this is going to be the adjoint caloric measure, again with a similar normalization. But of course, for the adjoint one, we want to take the backwards in time corkscrew point. Okay? All right. So then let me point out that if I take the omega measure or the omega tilde measure of delta star and take the average, it's going to be like 1. Right, because when you take this average, excuse me, you're just canceling this part out, and that's just the Bourgain estimate. This is the adjoint Bourgain estimate because you move backwards in time. You just change the time variable, make that change of variable t goes to minus t. Okay, it works the same way. Okay. All right, I'm going to also set k star to be the radon Nikodym derivative. Remember, by hypothesis, we're assuming that this guy is absolutely continuous with respect to this guy, and moreover, that this measures A infinity with respect to this measure. And we're also assuming the same thing for the adjoint guy. Okay, so with that preliminary bit of explanation, the next lemma says the following. Given epsilon bigger than 0, there exists a number m epsilon, which actually is going to turn out to be on the order of 1 over epsilon, such that there is a closed set f star contained in delta star with the following properties. First, f star is most of delta star. So the complement is less than, has measure less than or equal to epsilon times the full measure of delta star. Okay. Second, 1 over m epsilon is less than or equal to the average of k star with respect to sigma over the ball delta r of z. I'll say a word about that in a second. So in other words, these averages are bounded uniformly above and below. Similarly, for the averages of the adjoint Poisson kernel k tilde, except I don't need to put squiggles here. It's actual less than or equal to. And this is true for all z in the set f star and all 0 less than r less than the radius of, or maybe I even allow constant, r delta star. That is the radius. I don't know if I should call it a radius exactly because they're not really It's not a radius, it's a sort of a side length because they're cubes, not balls. Okay. All right. Okay. All right. So let's do the proof. All right. So remember the assumption is that K star, well, omega and omega tilde are A infinity measures, which means that K star and K tilde star are A infinity weights. Which means that they each belong to some AP class. One of the Muckenhaupt AP classes for some finite P. And we can assume it's the same P because the AP classes are nested increasing, so we just take the worst one. All right? Which means, in other words, if you're not familiar with AP, I'm going to tell you what it means right now. What this means is that uniformly, the averages of K star and K tilde star times K star to the minus 1 over P minus 1 to the power P minus 1. The product of these two averages is uniformly controlled, and this is for all delta contained in, let's say, 2 delta star. All right. And the same for K tilde star. All right. So now for convenience of notation, I'm going to set K1 to be K star, K2 to be K star to the minus 1 over P minus 1. K1 tilde equals K tilde star. K2 tilde equals K tilde star to the minus 1 over P minus 1. All right. And so then I notice that, remember by Bourgain, we pointed out the average on delta star of K1, which is K star, is like the average of K tilde 1, which is like 1. Okay? But then this AP condition here tells us that the averages of, if this is like 1, then the averages of the K2s must be also like 1. Okay? All right. And now I'm going to choose a cube, a dyadic cube on the boundary. Okay, digression for a second. The boundary sigma endowed with this surface measure lowercase sigma is a space of homogeneous type. As such, it is endowed with a family of dyadic cubes. Although since it's a graph, it's actually easier. You can sort of do them by hand easily enough. But there are dyadic cubes. There's a dyadic cube structure. This goes in this all fours regular context that we're in now. This actually goes back to Guy David. There was a more general construction due to Mike Christ. And there's a more recent construction of Huhtinen and Karama. who show in particular that there's actually a multiplicity of grids, and given a surface ball or cube of this nature, you can choose a grid such that, depending on this guy that you fixed here, you can choose a grid such that there's a dyadic cube containing this one of comparable diameter. Okay? All right. Let's call it Q star, such that diameter of Q star is comparable to the diameter of delta star, and which means that their measures are comparable. And delta star is going to be contained in Q star. Okay? All right. So all of these things that I've written here hold with delta star replaced by Q star. Okay? All right. So now we do a standard Calderon-Zygmunt stopping time construction. Okay? Okay, we're going to subdivide Q star dyadically, and we stop the first time that we get an average over cube Qj such that the sum K1 plus K2 plus K1 tilde plus K2 tilde is, greater than M, where M is a large number to be chosen in a moment.
Steve, I have a question. Since I think that these caloric measures are doubling, then couldn't you use just the standard cubes of Michael-Kris, for instance?
Oh, this is, yes, but I just wanted to choose a cube that contains the delta star.
Mm-hmm.
I don't know if in Mike's construction, does he necessarily say that there's a grid, that given a surface ball or cube, there's a grid such that there's a dyadic cube that contains the specified one?
No.
Maybe it comes out of his proof.
But perhaps, well, just a curiosity, maybe you could eliminate, I guess, the doubles of the cubes or something like that. Well, anyway, it doesn't matter.
Yeah. In any case, we do have doubling in this context for the caloric and adjunct caloric measures. So.
Thank you.
Okay. Although, in fact, I'm really thinking of constructing the dyadic cubes with respect to the sigma measure, not with respect to the caloric measure. So, yeah, I guess it doesn't matter too much. Okay. So in any case, then, let's see. So this was the criterion. So notice then that the sum of the measures of these cubes is less than or equal to 1 over m times the sum over the integrals of k1 plus k2 plus k1 tilde plus k2 tilde. The QJs are maximal, so hence not overlapping. So when we sum them up, this is going to be less than or equal to 1 over m integral over q star of this sum. And each of these guys integrated over q star gives you basically the measure of q star. So this is like 1 over m times the measure of q star, right? And now I can choose m to be on the order of 1 over epsilon, and I get this property 1 here. Okay? All right. All right, and now we'll prove 2. 3 is exactly the same as 2. Okay, it's the same proof. So let's let xt be a point in f star. I don't know why I wrote it with a fancy z here because we're really in Rn. Okay, I should have just written xt. Okay, so let's let xt be a point in f star. R be positive. Choose a dyadic cube. Contain a q star. Q contains the point xt, and the diameter of q is like r. Okay, so then by doubling, the integral on delta r of xt of k star is controlled by the average on q of k star, which is of course k1. But f star, remember, is the complement. I should have said that. I should have told you, sorry. F star is then going to be defined to be q star minus the union of the qj's. Sorry about that, I should have mentioned that. That's why one holds. Okay. So F star is the set where we never stopped in the stopping time construction. Okay. So therefore, all of these averages are bounded by M. Okay. All right. And then we have the similar thing for the K2s. The average on delta R of xt of K2, but I'm going to write it explicitly now. It's K star to the minus 1 over P minus 1. This is also less than or equal to M for the same, well, up to some constant for the same reason. All right. And since K star is an AP, we have that the lower bound, oh, by the way, the upper bound was immediate, right? The upper bound is immediate here. This is the upper bound in condition 2. And now we're going to do the lower bound by the condition AP, delta R of xt, integral of K star over, the average of K star over that surface ball is like 1 over the average of the surface ball of K star to the minus 1 over P minus 1. This denominator is bounded from above, so this is bounded from below. Oh, sorry, but with a P minus 1. So this is bounded from below by 1 over M to the P minus 1, which is like epsilon to the P minus 1. Okay? And that proves it. All right, any questions? Okay. Yeah, go ahead. I'm not sure if I'm understanding the question. Well, I'm just taking the worst one, right? They're both in some AP class. Maybe not. And the AP class are nested, so I just take the worst one. Right. And then they're both in the same one. But you don't have any relationship between. No, there's no. Our assumption is only that each one is an A infinity, so there's no necessary connection between the sharp class for each of them. If that's what you're asking. Yeah. Yeah, no, we don't. Yeah. Okay, we've just got about 5 minutes, so let me I can just make one more reduction before we take a break. Yeah, sure.
So is this maybe it's kind of for an equation of this, because this has some flavor of something that they use in the elliptic setting that essentially they call this thing where if they know that for every cube a fixed proportion of them are nice,
Yeah.
they can do that. Are nice in the sense of something like this.
Yeah, sure. Yeah, so that kind of thing, yeah, it's in that spirit. Except here, I guess I've erased the condition now, but the condition one, it wasn't just a big piece, it was a super big piece, like up to an epsilon. So that's kind of going to be convenient for us for the reason that I'm just leading up to now. Okay, but you're right. In the elliptic theory, a lot of times, yeah, elliptic or parabolic theory, a lot of times this is a useful thing that you know something is happening on a big piece. And it happens on a big piece for every cube, and then you can somehow self-improve that. It's like, I don't know, it's even in the spirit of, I don't know, John Nirenberg, that kind of thing, where you know a thing that happens in a scale invariant way on every cube somehow often leads to self-improvements. I guess that's what you're asking, right? Yeah, right, yeah. Okay. All right, so remember, we need to show that the half-order derivative is in BMO. So there's a so-called John Stromberg lemma for BMO, which works in the parabolic BMO case just as well. They proved it originally in the classical setting, but for parabolic BMO, and it says the following. It's enough to show that this guy is in BMO. It's enough to show that there exists a number n less than infinity such that for each parabolic cube QR in Rn, the infimum over all constant C of the measure of the set of Y and S in QR such that dn of A of YS minus the constant is bigger than n. That measure is bounded by theta times the actual measure of QR for some uniform theta less than 1 small enough. Okay? So in other words, if you can show that for each Q, right, there is a constant such that this set has measure less than this strictly less than 1 portion of the measure of QR. If you can do that for every Q in a uniform scale invariant way, then it shows that self-improves to give you that dn of A is in BMO. So in fact, the classical John Stromberg, in the elliptic case, you can do this with theta equals a half. I would have to look again to see if you can still get a half exactly in the parabolic case, but for sure, that's not going to matter for us because we're going to be able to make the theta small if we like, using this previous lemma.